In this video, we're going to be going through the cyclization of monosaccharides. So let's remember that a monosaccharide is essentially just a single unit of a carbohydrate or a monomer or a simple sugar. Let's remember that aldehydes can react with alcohols to form a hemiacetal. So we can see that in this reaction, a separate alcohol reacts with 1 mole of a variable alcohol in the presence of an acid catalyst to form a hemiacetal. Okay. However, when an alcohol and an aldehyde are a part of the same molecule, an intramolecular reaction occurs to form a cyclic hemiacetal. In this reaction, we can see here that a hydrocarbon containing both an alcohol and an aldehyde with a carbon chain length of 5 carbons will react in the presence of an acid catalyst such as tosylic acid or sulfuric acid to form a cyclic hemiacetal. And we can see here that the reaction goes heavily in the forward direction because the formation of a 6-member ring is favorable due to the cyclic hemiacetal ring being strain free. Okay, so we can go through the mechanism of how a cyclic hemiacetal forms. So we can see here that this carbon chain, right? This carbon chain will, in the presence of an acid catalyst, either being tosylic acid or sulfuric acid, will undergo a proton transfer where the aldehyde is protonated by an acid, and then we get an intramolecular nucleophilic attack by the hydroxyl group. We can see that this causes an arrow pushing mechanism that causes the formation of an oxonium ion, the oxygen with 3 bonds. 2 of these bonds forming with carbon, and the other bond forming with the hydrogen, forming the oxonium ion. The oxonium ion is deprotonated by the deprotonated acid, so a second proton transfer occurs, forming the hemiacetal, where we can see that there's an ether group here on one side, and then the other is just a regular alcohol. Okay, that's the hemiacetal here. Now, let's go through several forms of monosaccharides, and one such form includes pyranose. So Pyranose generally forms from aldohexoses, and pyran refers to a 6-membered ring with an oxygen atom incorporated into the ring. So out of those, so within the 6-member ring, it contains an oxygen atom as one of those members. And we can see that ose just refers or just indicates that the molecule is a carbohydrate. And so for the same reason, D-glucose being an aldohexose will favor formation of the cyclic hemiacetal. So we can see here that a similar reaction occurs because in the first reaction we simply just had one hydroxyl group with reacting with an aldehyde part of the same molecule. That's a part of the same molecule, right? So we can see here that in this that we see something similar here. It's just that there are a bunch of alcohols reacting, and we can see that there are a bunch of alcohols within the same molecule, a polyhydroxylated aldehyde or ketone, right? And we can see here that carbon 5 allows for the formation of the 6-member ring. So that's the reason why the hydroxyl group on carbon 5 is the one that reacts with the aldehyde to form the 6-member ring, because the 6-member ring is the most stable ring that forms it's considered relatively stable compared to its five member ring counterparts, as well as 7-member rings. So carbohydrates can also be classified into names based on in its ring form, and we would call this D-glucopyranose. D indicating that the configuration of the chiral center is furthest from the carbonyl group is R. Pyran referring to the fact that this ring that forms here is a 6-member ring, and then Ose demonstrates that, or Ose indicates that the ring is a carbohydrate. We can also refer to this ring as D-aldofuranose, where aldo just indicates that the aldehyde is a part of the chain instead of a ketone, and then furan is just a 5-membered ring with oxygen being a member, and then ose it just indicates that this is a carbohydrate. Okay. Now the mechanism that applies is the same thing. So we see that there's a proton transfer by the aldehyde deprotonates the acid, or the aldehyde is protonated by the acid. We can see that a nucleophilic attack from the hydroxyl group on carbon 5 nucleophilically attacks the aldehyde on carbon 1, which causes an arrow pushing mechanism, forming the oxonium ion, followed by a reprotonation of the acid to form a product. So before we get into steric configurations, let's first understand the concept here. So generally with carbohydrates or monosaccharides in their open ringed form, we can see that between carbon 2 and carbon 1, we see that they exhibit a degree of rotation at this particular bond between C2 and C1, and we call this mutarotation. So mutarotation just refers to the rotation of the C2C1 one bond, and we can see here that during mutarotation, the two stereoisomers of glucopyranose interconvert between each other, resulting in an equilibrium between the two isomers. Okay. And if we get into the specifics here of mutarotation, we can see that that two products can be formed. So there's a cis product where both the hydroxyl group of carbon 1 and the other carbon containing the alcohol on for carbons that's linked to carbon 5 are both facing up. They're on the same side of or we can consider the steric configuration of this monosaccharide to be beta. Conversely, if mutarotation occurs where the bond rotates, where the aldehyde functional group rotates, we can see that a different product forms where the product can be where the steric configuration of the monosaccharide here can be trans, and we would refer to this as alpha. And alpha refers to the fact that the substituents of carbon 1 and carbon 5 are on opposite sides of the ring. Now, we can see that these two isomers are considered to be a pair, and they are called anomers. Okay, and the carbon responsible for the stereochemistry of glucopyranose is called the anomeric carbon, or in the particular case of any Pyranose ring, or in the case of Pyranose rings derived from aldohexoses, it's carbon 1. And as I said before, because the bond between carbon 1 and carbon 2 exhibits rotation, we can see that um, each individual constituent of the pair, or we can see that um, one of the pairs exhibits a greater degree of rotation here. The alpha the alpha isomer, the alpha stereoisomer, or the trans stereoisomer, exhibits a greater degree of rotation in terms of rotating light. So, just to clarify, both of these stereoisomers rotate light in a dextro-rotary fashion. Both of these, but they vary largely to the extent of rotation of light they exhibit. So, in the case of beta D-glucopyranose, we can see that the degree of rotation is approximately 18.7 degrees, whereas with alpha D-glucopyranose, we can see that the degree of rotation is 112.2 degrees rotation. So when the mixture of anomers equilibrates, we can see that a new specific rotation is established, and we see that it is 52.6 degrees. Okay. Now, there are different ways to represent Pyranose rings. Haworth projections and chair conformations are such representations that we use, and we can see that Haworth projections are useful in showing configurations, but majority of the time Pyranose rings will normally be in a chair conformation. So we can see here that in beta D-glucopyranose, we can see that there's the Haworth projection shown over here, and then the two chair conformations, and we can see that one chair conformation is generally favored over the other, and it's usually the chair conformation that has all the substituents occupying equatorial positions, because generally speaking, any substituent occupying an equatorial position is relative to the same or to the opposite is relatively more stable than the opposite chair conformation where the substituent is placed on an axial position. Okay? So, just keeping that in mind, that most of the representations shown here will usually, or most of the reactions that react with monosaccharides, usually happen in this form. Any chair conformation that has the majority of their equatorial positions occupying any substituent occupying the majority of the substituents occupying equatorial positions. Okay. So there's another form of pyranose or monosaccharide in the form of a pyranose that can be derived from ketohexoses. So remember when we referred to D-glucose as an aldofuranose? We consider D-fructose to be a ketohexose, given that the functional group expressed for this particular monosaccharide is a carbonyl group, right? And so we see here that a similar reaction occurs, but instead of we see, or instead we see here that the same reaction conditions are favored, where in the presence of an acid catalyst and the formation of a ring, a six-member ring is favorable. It's pretty much the same pattern that we see with everything that I've shown previously. But one key thing here is to note which carbon is the anomeric carbon. The anomeric carbon in this case isn't 1 but 2, because carbon 2 is the one that contains the carbonyl or the ketone functional group. So we can see here that the same reaction mechanism occurs. There's a proton transfer followed by a nucleophilic attack, which forms the oxonium ion. The oxonium ion reprotonates the deprotonated acid, and we're left with two products due to mutarotation: beta D-fructopyranose and alpha D-fructopyranose. Now, aside from pyranose forms of monosaccharides, there's also furanose forms of monosaccharide. And furanose just refers to a five-membered ring with an oxygen atom incorporated into the ring. And ose just indicates that the molecule is a carbohydrate. So for the same reason, D-fructose will favor formation of the cyclic hemiacetal. By same reason, I mean that because there's a carbonyl group and an alcohol in the same molecule, there's the favoring of the formation of the cyclic hemiacetal. So the general reaction. So as I understand, it appears that only Furanose rings form only from ketohexoses, and the anomeric carbon for ketohexoses is still the same. It's still carbon number 2, right? And we can see that formation of the five-member ring is favorable due to the ring containing minimal strain. It's not experiencing less strain relative to a six-member ring, but it's still an it's still a minimal amount of strain, enough for the reaction to be favored in the forward, or for the forward reaction to be favored. So the formation of ketohexoses is the same as the previous forms of cyclic hemiacetals. We can see that there's the presence of an acid catalyst, the anomeric carbon, the same a very similar mechanism, right? Where there's the formation, the key formation of an oxonium ion from a when it nucleophilically attacks the carbonyl group that's protonated. And we can see here two products: beta D-fructofuranose and alpha D-fructofuranose. Okay. And if we were to break the name down, we would see here that D-fructofuranose, D just indicates the conformation of the chiral center furthest from the carbonyl group is R. Furan just indicates that the five-membered ring with oxygen is a member, and then ose just indicates that this is a carbohydrate. Similar naming system we see here: D-ketofuranose. Keto just refers to the fact that that the ketone is a part of the chain.